So we are going to continue with the next module, which is concurrency. So that we can see how to automatically manage concurrency without necessarily having to declare logs and synchronizers, so that we don't need to manage them manually on our own. There are classes that have already been given to us, which we can use to manage logs and synchronize our code. So we should be able to use atomic variables, reentry, read, write log, concurrent collections, and executor service, which is to manage thread groups. Okay. Then finally we will be able to do an example of function using function memo, of course with executor service. So this package we are working with at the moment is called Java Retrieval Concurrent. We are not doing the runnable and extending thread anymore. We are using concurrent Java Retrieval Concurrent package. Okay, so that we can be able to manage thread groups, which we can assign different tasks. Then they can finally revert back with a result. Okay. Now, similarly, on the other side, we had the keyword volatile. We had the keyword volatile, which we use to protect fields for synchronous access. Now, for this package, for this concurrent package, we use atomic. For example, in this case, atomic integer AI, new atomic integer 5. If AI will compare with 5 and 42, if they're comparing, then we say system without less than 40. Now we want to modify the value of this integer. But before we modify, we check first if it is equal to a certain value. So that if another thread modifies it, then we would be able to tell, we can just take a different answer. But if they are comparing, then we will replace it with 42. So it's a way of checking if it is checking for consistency in that part of the thread that is executing at that particular time. Then on the other side, we were using synchronized to synchronize a section of code, a method. But on this case, we're using a write log, or you can also have a read log. So you can be able to create that, apply a write log or a read log to a certain section of code. So if you are dealing with a shopping cart item, then we would protect this section of code. That means only one thread can add at a time. Only one thread can access it. It is more or less like the synchronized code block sections, but this approaches it in a different way. So you declare a reentrant read write log. Once you have it, you can apply it to log some sections of your code. So this one approaches with a different syntax, but it more or less tries to achieve the same thing. Then you can have read log. So this could be an improvement of the other one, because the other one, it doesn't matter if you are reading or writing. Once it's synchronized, that's it. Whether you are writing or reading. But here you are able to specify whether you want a read log or you want a write log. That is the flexibility that you can have with this concurrent logs package. Okay. So this one has an advantage because you can choose when to apply a read log and when to apply a write log. Then there are several classes that you use for synchronization. There's a semaphore class, and we also have a countdown latch, and this is a simple utility that you can use to give signals and events. And then you have cyclic area, parser. We'll be able to see how to use most of this as we synchronize our applications. Okay. So for example, for cylinder barrier is an example of synchronized category class, which is in this package. So final cylinder barrier, you have two threads must wait before they can unblock. You specify the number of threads which have to wait. Must await before they can unblock. And so that is how you apply the latches, the synchronizers, the semaphores, the phasers, and that. But most important on this module is the executor service. The executor service, which is most critical point in this module. And the executor service is used to execute tasks. It eliminates the need. You don't have to create threads manually. Like the one we were saying, we have to instantiate an object of a class, then we start the thread manually by saying we start. In this case, we don't have to do that. We can just create a pool at once of threads, which keep waiting for tasks. Once they finish, they return back to the pool to wait for other tasks. Okay? So tasks might be executed in parallel depending on the executor service implementation. So tasks can be runnable or callable. There are two different things we need to distinguish between these two. When you are using this runnable tasks, they will not return a result. But if you want to collect a result out of your threads, then you use concurrent.call. So, and this is we create the instance of the service as this. And you can now apply it to different tasks. So callable interface defines a task to be submitted to an executor service, and it says with subsimilar to runnable, the result using this returns a result using generics. We looked at generics earlier, and we said it is a class that expects an object of any type. You can define the type later. Then, how do you collect results from your executor service? You use something called, you have to implement the future interface, which will hold for you the result. Where will the thread update once it is done executed? Where will it update? You have to keep a place where your thread will be updated once it's done executing. So you use the interface feature. The feature interface is used to obtain the result from a callable process called. So that is where, if you submit an array which is divided into chunks, which is then given to different threads, once that thread is done, where does it update? You have to provide that for your executors. And then you can shut down an executor service once we are done using it. Of course, after declaring like this, therefore, we can shut it down once we are done using it. Shut it down like so. Shut down. And if it will not shut down automatically, you just issue the command shut down. But maybe some threads are still running, processing some tasks. That means you have to wait for some time before the threads can finish. Because you might issue the command shut down while some threads are still processing some data, and you don't want to lose that data. So it's best to wait for it to terminate for maybe 5 seconds, like for this case. Then you can now, that is the time you are sure the service has, the threads are finished executing. So once you start and execute a service, you make sure you shut it down. Notice that there is nowhere we have said thread to start. It is automatically called. Okay? So for example, this is an application that tries to, like the one we planned for sockets. It opens a number of sockets on the client, and it also opens a number of sockets in the server, corresponding number. So each socket, each socket on the server receives a request from the client. We send a request to each socket in the server that is covered. So for single-threaded applications, you have to wait for, you have to look through for each port, and one thread will be doing the looping and the port for executing the connection to the server. But when it comes to a multi-threaded application, create your executor service like so. So this is your thread. Now this becomes your thread. Thread pool used to execute collaterals. And then you have the result. Where will the result be saved? You create there. Every thread, when it terminates, where does it take its result? It should take it to maybe this one. Okay, this is a collection, right? This is the thread. This is where the threads will report to. This is where the threads will update. So a map used to connect the request data with the result. So once the thread is done, it should bring its data. Okay. Then look to create and submit a bunch of callable instances. Yeah. Request response, you start a request to this host at this port, and then you say network line collabo, network line collabo. Then futures equals to ds to submit, callable look up future. Now when it's done, where does it update? So we need to know how that is affected. How does it do the boot? Then of course once you are done, you need to shut it down. It is best practice to shut your services down. So network client. This is where we get the results after submitting this code. Look through to create and submit a bunch of columns. This is where we wait for them to get up to give us a result at this point. Okay. That is where we wait for a response to be given to us, and then where we update our. Of course, we are getting the result from the future, which we say it's an interface for capturing results from different threads that are being executed. Once you get your result, then you can update your map. Yes? You're fine. The other aspect is parallelism. Parallelism is where we notice that nowadays we have several, either most machines have cores or they have multiple processors. Two I5, I6, I7, I3. So how do you say you want to submit a task to be done by a certain process? And you say the next task again will be done by another process. Okay. So this will introduce us to how parallelism, this is how now we can submit our tasks to different. You have task 1, 2, 3, 4. Each one of them has data. For each task, we create a thread which will be served by a particular CPU. Because we don't want all the threads to be served by one CPU, because we will be wasting these processors. We want to take advantage of all these processors because they could be idle or they could not be having someone to do. So we want to say every task we create a thread which is then served by a CPU, task is served by CPU, task by that task, like that. And then also how do we get the results back? The CPUs, because this you never know, this one might be having a lot. Ordinarily they should have the same speed, but in practice there has to be there will be some errors of some sort. So this one will execute a bit lower, although in terms of the CPU time, not human time. So this could finish early, this could finish late, this could finish earlier than the other. So you need a way of collecting the results from your threads, which have been executed by different CPUs. So at the end of the day, we have to collect. So this comes in with the four-chain framework, where we split data sets into equal-sized subsets for each thread to process. And we are saying that there would be a problem because CPUs might have different speeds. Now Java does require CPU time and may reduce the time available for the thread to be executed. The data that you give to a certain CPU may need more time than another. Or the data that you submit to a certain thread will need less time than another. So you can have those time differences in terms of when they finish. Okay. So this is very key to that. Then we have the idea of what still keep multiple threads busy. Divide the data to be processed into, so you divide the subset into small sets. For a number of sets, assign the data subsets to a threads processing queue, which will be taken up by several threads depending on how many they are. Each thread will have many subsets queued. So you could have many threads taking up all 3 tasks. One thread can take 5 tasks. Another thread can take 10 tasks, depending on how big the subset is that you are dividing to process. If a thread finishes, it can also pick tasks from another thread, which is doing some other work and submitting. So it's actually a question of making use of your processors, all your processors at once. So for example, in this case, this will be a single threaded application, and we have this array, which is about 1 G. That array will be 1 G. It will be huge. Although it's an array of integers, but it's pretty huge. Yeah. It's an array that takes that much. So we want to process that. And we look through it. This is now a single threaded application going through that array. This one will fill up the array with random values. this one sequentially set the array for largest value. After you fill, you search. Okay, after you fill, you search the value. So instead of having one thread to do that, especially the searching, we can split that array into maybe 10 parts. Then we assign each thread to search the 10 parts. Okay? So how does this work? If we split, let's say 20 integers are in an array. We split them into 5, 5, 5. We'll have how many threads working on those? Thread 1, thread 2, thread 3, and thread 4. Each of these threads will come with a greatest value in its set. Then we will have how many numbers to compare? 4, right? Then either of these threads can take up that task of comparing the remaining 4, or these threads can take up to compare the results for this or this. But this we are not talking about 20 integers here. That is massive. So we will have several threads doing that. After these threads report the integers they have come up with, the greatest integers in their set they have been given, those integers will form another array, which is again split and given up to the same threads to do the search. Okay? So here we started with an array of 20. Now we have an array of 4. Then this 4 can be taken by one thread. So that is one way of doing that. But in this single thread application, everything is done by one single thread, which will not be as efficient as possible, and yet we work for processes which are idle. So a fork chain task represents a task to be executed. Task contains the code and data to be processed. So it has a code and data to be processed, similar to running a code. And we are saying a huge number of tasks are created and processed by a small number of threads in the fork chain pool. So we have a pool of threads in the fork chain pool. So a fork chain task typically gets more fork chain instances until the data to be processed gets subdivided. That's why we are saying this one will report, we form another huge array, which will then be subdivided until we get the last number, which is greatest of all. That's such. So we cannot avoid recursion here. Recursive functions. They exist even in C++. A function that calls itself, right? It's a function that calls itself until a certain condition is done. So there is also what we call a recursive action. It is same thing. It will be calling itself as a process. So when a task does not need to return a result, then recursive task, when a task does need to return a result. So you use, depending on what you want to do. Action will not return a result, but the recursive task will return a result. So recursive task example, we have our array here. So public classify max task. Recursive task. So recursive task will return a result, like you see there. Recursive task will return a result. But so we have our array here, final means you cannot change after it has been initialized. That's we saw that the other day. So public find max task, if you have an array, you have the start position and end position. Then you have a compute which where the work is done is zero. So when it's done, the return type will be an object of type integer, not primitive type. Okay. So when you are computing, you need to split data. If data is small enough, process data, you don't need to do anything. Else, you need to split data into parts so that you have left data, then task 1, task 2, new task, then you are assigning the right data. Then you combine the result of this and this. Okay. So we have how many tasks? In this case, 2. One is taken left, another one is taken the left data, another one is taken right. So we've split this array into 2. And after you take them, we can combine the result. We can combine the result like this. We can combine the result with task 1. Block until done. So it will give us another array which we can then split up again. So this is the integer compute thing that is being called, which looks through that up to the end. Doesn't looks for the maximum value. Okay. So compute above +1 +2. So we rather look at the example there so that we can be able to comprehend properly, especially for this example on fork join, which divides up an array, gives us a result, which we then combine with others until we get the maximum value. We divide a set into a smaller set as we recursively search. That's it. So that would be we have executed a service solution, which is a class of arrangement, the one we just did. But if you want to go straight to the fork chain map solution, then we can open this so that we see how this array gets split and then how they are assigned to several tasks. We can then put the result back.
Practice 1 and 2 practice.
Sorry?
Practice 1 and 2.
Practice 1 and 2. There are only 2. So you check the first one, you have a server and a client. Basically, you have 2 packages in the same project.
This time it's 2 packages in the same project.
Same projects. Practice.
We call the project concurrent. We call it concurrence.
Code, yes. Concurrent 01, 02. The other one will be 02. So we want to see how things how we get initialized, how we get call the various what it generally tries to do is to have a server with open box, then try to submit tasks to which are then
Oh, you want to That's fine.
It's not okay. Hey.
So,
Okay. What was the problem? You just you had a problem with this. And I have software for this problem.
now, when we did it, the regions were very some of those swing activities that that's what I want. They don't have way back. No. So then you find them what is that?
Very important. Very